In the previous video, we considered the dynamics of this motor system under the situation in which it was under current control, which is to say this current going in here was modeled as an ideal source. And in that model, it had the motor had the very nice feature that its torque output was almost identical in behavior to an ideal torque source, which is to say that the torque coming out of the motor and into the load here, this T, was almost entirely independent of the speed of RPMs, this omega that the motor was spinning at. And this can be attributed to essentially that this source here, all the torque that it produces goes right through this serial resistance in series with the source, because this source is a through variable source, a torque source, which is like a current source. So all the current going through here, all the torque coming out of here goes right through this unaltered. Another way you can think about this is this ideal torque source is varying the RPMs as necessary here to mitigate the effect of this RPM drop across this resistor. Or in electrical terms, it's keeping the voltage at such that the current going through this resistor remains constant regardless of the voltage that needs to be put here. So the downside of this, making your motor into an ideal torque source like this, is that the power supply needed to do this ends up being somewhat complex, costly, and or inefficient. So much more often you will be doing a much simpler control where this source is instead a velocity source, which is to say a voltage source, which is a cheaper type of power supply, turned into a velocity source through the transduction of the motor. So this is cheaper, but it's a bit more complicated. So let's now analyze voltage control here. So voltage control. And this is the kind of more cheap but slightly more complicated to analyze case here. Typically, this is done using a transistor that switches on and off very quickly. This is known as pulse width modulation. Or PWM. And the ultimate voltage source coming out of your pulse width modulated transistor, the voltage coming out of it ends up being proportional to the percentage of time that the switch is on versus off. One other remark here is that we need to make sure that the switching frequency, let's call it the frequency of switching, PWM, that needs to be rather larger than 1 over this mechanical time constant associated with the system, so that you don't see any ripple coming through the motor. Though sometimes you might hear the motor hum though. But usually this isn't a problem. So So for example, I used to have an old Toyota Prius, which is a hybrid electric gas car. So it had an electric motor in it. And when you push on the gas, you would hear a little hum. And that hum was at about 20 kilohertz because the PWM frequency of the motor controller was at about 20 kilohertz. These days, they've gotten better transistors and they switch faster, so you often the humming is supersonic, so you don't hear it anymore. Okay, so that's the practical matter of voltage control. Let's now analyze voltage control here. So what we want is a model for really this angular velocity that we see here when subject to, in this case, this source is this velocity source driven by it's actually a voltage source, but it turns into a velocity source through transduction of the motor. And so there's a velocity drop across this resistance, and then some other things here, but we want to calculate what this is. So the way we're going to analyze that is we're going to use the loop law, also known as Kirchhoff's voltage law, which is the sum of the voltages around a loop is always equal to 0. So we have a voltage rise here, or a velocity rise, up to omega s, which is what this is, and then we have a drop across this resistance, and then and another drop from here down to ground. So this we know is omega s, and what's the drop across here? Well, it is the product of the torque going through this resistance times this resistance here. That's sort of like the voltage drop across a resistor is the current times the resistance here. So let's write that down in an equation form here. So loop equation. We get the voltage coming in is omega s, and then that is equal. Let's just say if we subtract out all the velocities drops after that source voltage velocity, they should sum to 0. So here's the source coming in, and then we have a drop across that resistor, and that velocity drop is equal to the magnetic torque, right? That's the torque going through this resistor times this resistance here. So it's Tm times R over K squared here. And then we have one other velocity drop, which is just that omega, that is the one we care about. And the sum of these velocity drops is equal to 0. So we can rearrange that to get that our angular velocity coming out of the motor is equal to this minus R over K squared times the magnetic torque Tm, plus, and now I'm going to take this omega s and turn it into what we actually are supplying, which is the voltage source. So I'm going to write this as 1 over K times Vs, our voltage source input. Okay, and I'm going to label this one because this one's kind of important. This tells you what the velocity is as a function of two things. One, this voltage here, and the other is the magnetic torque. And you can think about the magnetic torque as kind of the ideal torque coming out of the motor before you consider drag due to the bearings and air friction and things like that. So let's plot what this looks like. You can kind of think of this as a velocity which has a let's see, let's just say this turns into a line where this is the slope of the line and this is the intercept. So let's draw that now. What we get is a torque speed curve that looks something like this. Where over here this is by convention, torque is drawn on the x-axis for motors because often the thing you care about getting out is the torque. And then you're kind of asking how much velocity do I get as a function of that torque. So here's omega here. And so this equation looks like a line that has as its intercept here Vs over k, that's the intercept here. And I'm going to draw it as a dashed line that slowly goes down here. And so here is this here is the slope, and this I'm going to do it dashed because this is kind of this ideal magnetic torque coming out of the motor before you consider drag here. So as you increase the torque, the angular velocity goes down. So this corresponds to when Tm is equal to 0. This is this so-called omega 0, where there's no magnetic torque. This is the hypothetical speed that motor would go if there was no drag acting on it. Okay. Let's see here. And then over here, and then the slope is equal to this guy here. And then over here is, this is when omega is equal to 0. Right, omega is equal to 0. What's that? That is then where if you solve for that, Tm is going to be just k over RVS. So when this omega is equal to 0, we just equate these two, and we get this guy here. Okay. So what next? Yeah, so this is Tm. This is this ideal torque. Next, before I talk more about kind of the upshots of this, let's bring in the effect of actual real drag here. Oh, one other thing before I get there. You'll notice Vs appears both here and here. And what that tells you is that as you increase voltage here, that kind of pushes this whole line out there. So that's how you can kind of get more power out of your motor, is by cranking up the voltage. So that's kind of your lever, your control. You crank up this Vs and you get both higher angular velocity and or higher torque, or just this curve changes, moves outward here. Okay, so next we need to think about the real torque you get. This is the ideal magnetic torque. The real torque is the torque that you get after you have subtracted out these kind of parasitic torques due to Coulomb friction on the motor bearings and this velocity-dependent drag that's due to either air drag and also eddy currents actually inside the iron core. So these are the two sources of drag, and what that looks like here is it just pulls the actual output drag down. So I'm going to draw that here. So we have this drop here, and this is this bearing torque and the Coulomb bearing friction, the Coulomb friction and the damping. And so what you really get is this other line that looks a little different, and it's lower actual torque than the ideal magnetic torque. And it's usually not quite parallel because you have this velocity dependent torque and this fixed torque, so it's a slightly different angle like that. Okay, so this is the real actual torque you get. This is T. And so just using this visual equation here, we can also derive this with a node law up there. You get that the real torque is equal to this ideal magnetic torque minus this damping torque and minus TC. And we can actually write that kind of helpful here to write out what those are. T bearing is going to be B times omega. So this is a velocity dependent drag, and then we have also the TC here. So I'm going to label that one here. I'm going to give that a number 2 because we'll see that. Okay, so that's the real torque. It's this torque minus Tm minus these drag terms. Okay, so this is actually our torque speed curve coming out of the motor that actually is a useful one after we've considered drag here. So let's now think about what this looks like. So this is a continuum of torques and speeds that you get for a given voltage here. So for example, over here, this is when, like, imagine you have the motor spinning like this. This is, the motor is stopped. Actually, I'll use a different color here. So the motor's stopped, and this is the max torque it can apply here. So imagine you turn on the motor, but you're holding the axles still. This is the stopped condition. And this is actually the maximum torque you can get here. I'll just label it here. This is the max torque. It's called stall. And it's called TS. Stall torque here, so this is TS. So that's the max torque at zero velocity. Then imagine you let go of the motor, and you start letting it spin. This, maybe you're somewhere here, apply some friction. So depending on how much friction you apply, the motor will spin faster or slower. It'll be somewhere on this line here, but you're always going to be on this line. You apply this much friction, this will tell you how fast you're going to go. And then maybe the last thing you might do is you just let go of the motor, and that's here. This is when you let go. So this is free spinning here, and this is known as omega F, free spinning. That's that guy there. Okay, I'll actually show this in a video. Okay, so here's that motor. I have it running freely now. Got it connected to the battery. So now let's go through those same three cases. Here's the first one. I just push my finger on it really hard. It just totally stops. That's the stall condition. I don't want to keep it on that for too long because the motor starts heating up, and I can burn it out pretty quickly actually. So this is a stall condition, max torque, minimum RPM. Now the next case, maybe I put a little bit of drag on it with my finger here on the axle here, so it's going kind of slow like this, some intermediate speed. Kind of hard to see, but it slows down, applies more torque like that. I'm applying some just drag with my finger. And then the last case is I release it completely, and this is free running speed. So unlike current control, where torque is basically independent of angular velocity, here under voltage control we have what amounts to a continuum of different torque angular velocity combinations that depend on how much friction you're applying on the motor. The less the friction, the faster the motor runs. And this equation here tells you this exact relation between how much friction you have and how fast the motor is going to spin here. So now we've answered some of those questions about how fast the motor is going to spin. Depends on the drag you apply, and some of these coefficients that we will see in a little bit how to figure out their exact value if you don't have them on a data sheet. But what I want to talk about first before we identify the motor, if we don't have the data sheet, is some other aspects to this torque speed curve, one of which is the power and efficiency you can get out of a motor. So the first subject is power output. Actually, before I do that, I'm going to start by saying it's convenient to express So let's say it's convenient. Terms of measurable quantity omega f, this free spinning speed that the motor spins at when it has no torque. So let's combine equations 1 and 2 to derive the torque speed curve in terms of this omega f here. Okay, so I had in equation 1 here above, I had this guy here. Let's start from that. And we had actually, I'm going to start from this equation here because that's how I have it written down here. Starting from this, I have 1 over k times Vs. And then for this Tm here, I'm going to replace that with what we got above. We have this r over k squared, and in place of Tm, I'm going to write this equation we used here, rearranging this to get T instead of Tm. So this is T plus B omega plus Tc, and that equals omega here. Then we would need to do some rearranging to get things into. We have omega appearing twice, so we have to do a little bit of rearranging here. So I'm going to write 1 over k Vs minus r over k squared times T plus Tc. And I'm going to move this omega term over to the other side. I'm going to leave a little gap here. And omega times, I had the 1 over there from this already, but also now we have this Br over k squared plus, sorry, this is the plus, like that. Okay, and now, okay, this looks like that. And now I'm going to multiply by the same thing on both sides to get some simplification here. I'm going to multiply by k squared over k squared plus Br. Same thing on this side, k squared over k squared plus Br. And I'm going to get, that's going to cancel with this guy here, and I'm going to get an omega on the left is equal to 1 over k squared plus Br times, now I've multiplied by k squared, so I get, instead of 1 over kvs, I'm going to get a kvs. And then here I'm going to get minus r, and I'm going to break it out into RTC. I'm going to leave this together here, like this. And then I'm going to have this other term, which is the 1 over k squared plus Br times RT, because actually I care about T here. Okay? So what we can do now is we have this about the torque produced by the motor and these other things that are kind of inputs or fixed like this. So one thing we can say is, well, if our torque is 0, then this term drops out, and then we can conclude that this guy is this free running speed that we wanted a relation for. So this is our free running speed here, right? Just set this torque is equal to 0, everything else is just constants, and we're left with this. Omega is equal to omega f. So this is omega f. And so now we can express our torque speed curve in terms of this omega f, because that's kind of convenient. So we get that omega equals omega f minus r over k squared plus br times t. And we're going to label that with a 3 because that's kind of a useful equation too. Okay. One other thing we can derive from this is, makes it easy to derive what the stall torque is. So let's also write also. So this is the free run. There's a free running speed here, this thing here. Let's derive what the stall torque is, because that's useful too. Ts, which is equal to the torque evaluated when omega is equal to 0. Not when t is equal to 0, but when omega is equal to 0. That is equal to, setting this equal to 0, then we get that it's just this times the reciprocal of this, so we get that it's k squared plus br over r times omega f. So that's also kind of useful to have. I'm not going to box it, but it's we'll come back to this. So that's its stall torque here. Okay, in terms of this omega f. So now, with these in hand, we're ready to derive some properties of power and efficiency of the motor. So power output. Let's put this on the next page. Because I will need some room. Power output, we'll call it P, is equal to, what's the power output? It's the product of the torque coming out of the motor times the angular velocity of the motor, torque T omega. So we'll just do T and then omega. We'll use this equation here. Omega equals this. So omega is equal to omega F minus this here, R over K squared plus BR times T. Make sure I got this right here. Yeah. And that is equal to T omega F minus T squared times this thing here, R over K squared plus BR. All right. So this is going to look like an inverted parabola, because we have a minus T squared there, and then we have a T there. So it's going to be, well, let's just draw what it looks like. We're going to plot T on this axis, but we're going to have a few different things we're going to plot on the vertical axis, so I'm not going to label that one. So the power, I'm going to draw in red. This equation here looks something like this, goes up, and then loops back down, something like that. And it hits, it goes down to 0 at this Ts, the stall torque, and it has a peak somewhere over here. So that we'll label this as P, power output of the motor. So it peaks somewhere in the middle. It doesn't, power is not, oh, and let me also draw here, just, here's our original torque speed curve here. This is our omega, there's omega. Okay, so somewhere in the middle. As you can imagine, it's a torque times the angular velocity. Their product peaks somewhere in the middle here too. It actually peaks right in the middle. Let's show that though. Where is P max? P max happens when this dp dt, the derivative, is 0, equals 0. Where is this derivative equals 0? When the derivative is 0, that's going to be the peak here. So taking that derivative, we have that derivative, taking the derivative of this power equation here by dt. Take the derivative of this, we get omega f. We're going to set this equal to 0. 0 equals the derivative of this, and then we have this taking the derivative of this, we get 2t times r over k squared plus br, and that's equal to 0 here. So we get that t is equal to 1/2 this k squared plus br over r times omega f. So some factor times omega f. And it turns out if you look at what is this? Let's see if we've got anything else up here. Aha. Stall torque is k squared plus br over r times omega f. This is 1/2 k squared times br over r times omega f. So this turns out to be 1/2 of the stall torque. So in other words, the peak power happens right here in the middle. Ts over 2 is where P max is. So the max power happens right in the middle, and it turns out you can actually show as well that it happens at omega is equal to 1/2. Omega equals 1/2 omega f is also the case. So it happens halfway through. That's the peak power. Okay. We can also talk about efficiency. And efficiency, and I'm going to derive it as a function of the torque. And the efficiency is defined as this P out divided by the amount of P coming in. And how much power goes into the motor? Well, we can equate that to P in is equal to P plus these losses. So one of the losses is this frictional power, and the other one is this thermal losses due to heating up in the coils there. So these are the kind of sources of losses. This is eta, efficiency. And we can also use some of our equations to derive exactly what that is. I'm not going to write it out exactly what it is because it is kind of complicated, but I'll provide the path to derive it if you really wanted to derive the equation yourself. The power out is equal to, again, T times omega. And the power in is equal to the electrical power in, which is the current going into the motor times this voltage source being applied to the motor. So we actually know this relation here. We have it here. And we know Vs, but we don't know I yet. So how would we find I? I'm not gonna write out what this is, but we can approach if we wanted to. would be to use that I is equal to Km, sorry, it's equal to the torque coming out of the motor divided by K, and then we can write that's 1 over K, and what's Tm? It's this full torque output plus this B omega plus Tc, and then here omega appears again. You don't really want omega, you want it in terms of only in terms of T, so you would substitute in this equation 3 here above, and that from that you should be able to get I, and then you can plug it in there, and then you get an efficiency curve. Okay, so I'm not going to write that out, but this is what it looks like. Okay, so what is that efficiency curve? I'm going to use green here. The efficiency curve is a bit more complicated than this inverted parabola. It actually looks something like this. And then it peaks somewhere at a lower RPM usually than the max power, and then it also trends down and drops to 0 here. Of course, you're getting zero efficiency here because the motor's not spinning anymore. So that here's efficiency eta here. Okay. This is anywhere from 30% for small motors to maybe 90% for large motors, depending on the size of the motor. Smaller motors tend to be less efficient. Okay, so that's efficiency, and so maybe I'll just make some remarks here. We get better efficiency at high RPM over here, but you get that higher efficiency at the cost of lower power here. So you're trading off efficiency and power. So maybe if you want to get max power out of your motor, you want to operate here, power to weight ratio, for example, in a setting where the mass of the motor matters a lot. Otherwise, you often want to probably sit over here at the max efficiency point here. So why does efficiency kind of peak over here instead of here at the peak power? That's because of heat dissipation in the coils. That deserves a closer look. So heat dissipation in the coils depends almost exclusively on the torque output. And you can see if you look at the dissipation. So there's P dissipation. It's equal to, what's the dissipation in a coil? It's equal to the current going through the coil squared times the resistance, or let's say the dissipation in a resistor, which is equal to the dissipation of the resistance of the coil here. So that's the dissipation there. And okay, so it depends on I squared, and if we substitute in the torque instead of I squared, we get, so I is equal to Tm over K, so we get Tm over K, that's equal to I squared times R, and that is pretty close to, Tm is usually pretty close to the actual torque here. So I'm just going to write this as R over K squared times the torque output squared. So in other words, dissipation in the coils is not depending on the power, it's actually depending only on the torque here. And that's convenient because then, okay, we have dissipation as a function of torque here. So that means we can draw it on the same plot here. And it depends quadratically on torque. So what that looks like is something like this. It gets worse and worse as you get higher and higher here. So this is P dis. This dissipation here. So is the primary source of loss. Let's see, I'll do it here. And this is the reason why this efficiency curve looks not so good over here, is because this dissipation is getting worse and worse. So the other aspect to keep in mind about this is that this dissipation is actually, in practice, it's the key limit to torque production. And that is as follows. Your motor is subject to, it can't overheat. So what that means is there's only so much torque you can apply continuously before it overheats. And so often what that looks like is some sort of go, no-go line here. And just hypothetically, it's actually over here to the left of the max power. So this would be this kind of limit where over here, if your motor is applying this much torque, you're kind of okay. But anywhere to the right of this line here, this is meltdown. So you often cannot run the motor continuously above the max power. You have to keep it below this thermal limit dictated by the amount of torque you're applying here. Okay. I think that might be a good place to stop for this video. We'll come back and talk about in the next one how you would identify the motor without having the data sheet in front of you by measuring its current and voltage and things like that. And then we'll have a little bit to say about how you use these models.